Hello, my name's Filip Klubicka. I'm a postdoc at the Adapt Centre, Technological University Dublin. I'm a white male, use he/him pronouns. I have short brown hair styled in a messy fringe. I'm currently in my home office wearing glasses, a red checkered shirt over a black t-shirt, and today I'll be presenting my recent paper titled Probing with Noise, Unpicking the Warp and Weft of Embeddings. To start off, I'll kind of recap briefly what probing is, although I'm sure most of you already know. Probing is a linguistic classification task which uses vanilla language embeddings as an input to a machine learning classifier called the probe, which predicts some linguistic property of interest, such as sentence length, verb tense, subject number, etc., whatever. So the intuition essentially is that if the probe performs well, then the relevant knowledge must be encoded in the representation. Now, there are some limitations and challenges here, and in fact, the limitations of the probing framework have been extensively studied in the literature, and we kind of look at two in our work. One of them being, how do you actually determine whether the probe performs well? Because probe interpretations are inherently comparative. They depend on a comparison to another embedding model, to another encoder. This essentially makes probe evaluations extrinsic, or I guess just, dependent on another encoder. So our goal is to kind of move towards an intrinsic probe evaluations and develop an approach that can allow this. Another thing we're interested in is the embedding norm. There has been a lot of work analyzing vector dimensions as carriers of linguistic information, but the norm is rarely studied in this context and is often overlooked in a lot of NLP approaches and methods. For example, when you calculate a cosine similarity, you have to normalize the vectors, and this removes any information that may have been encoded in the norm, if there ever was any. So our goal is to explore the role of the norm in encoding information. One concept we found particularly helpful in thinking about this is the concept of information containers. Because embeddings are essentially vectors which are geometrically defined as having a direction and a magnitude. Direction being the coordinates in the space that the vector points towards, defined by the dimension values, and the magnitude being the length or the distance from the origin of the vector, which is defined by the vector norm. Because of this, we argue that an embedding essentially has two information containers, the vector dimensions and the vector norm, which are the warp and the weft from the title of the paper. Imagine two vectors pointing in the exact same direction, but having drastically different magnitudes. Right? For example, in this illustration, the vector for Apple is very short and the vector for New York is very long. If these two vectors were pointing in the exact same direction and we calculated a cosine similarity score between them, we would conclude that they are identical, even though that would completely disregard the stark differences in their magnitudes. Because of this, we also argue that essentially embedding models might be capable of encoding information in the norm of a vector, and a probing model might be able to pick up on this and use it as a discriminative property when making a prediction. Our goal then is to extend the probing method to be able to analyze the impact of the norm in encoding certain linguistic information. We do this by extending quite literally the sort of basic probing framework, which looks like this. What we add is an extra few steps at the end of this. So instead of looking at the result of 6 as kind of the end of the evaluation, we use that as the vanilla baseline. We then introduce systematic noise in the embedding, the goal of which is to disrupt the encoding in the embedding. And then we repeat the training, evaluate, and compare. And the idea is that if the performance of the probing model has dropped after step 7, then that means that we have removed some information from the embedding. There are 3 aspects that kind of make this method. First, and most importantly, it's the choice of the noise that will be injected in the embeddings, which helps ablate the information from the norm or the dimension container. But also the random baselines help us form a basis for our relative intrinsic evaluation. And then the confidence intervals are used to inform our inferences and provide sort of statistical significance measurements for the observed differences in the averages of the scores. First, the systematic noise. Its goal is to ablate a vector's information container individually. So whatever noise we introduce, if we're trying to understand what the impact is of the norm or dimensions on encoding information, then the noise cannot disrupt both. It only must disrupt one. And the solution that we've come up with is essentially a combination of random sampling and scaling. So in order to remove information fully from the dimension container of a vector, we generate random dimension values in the same dimensionality of the original vector, and then scale them to match the norm that the original vector had. That way, the vector dimension information will be complete nonsense, but the norms in the dataset will still be the same. On the flip side, if we wanted to remove the information from the norm container, we can take existing dimension values from a vector and then scale them to a randomly generated norm. While the values themselves will be different in this case, the relative differences between them will be the same, and as a result, the vector will continue to point in the exact same direction it pointed before we scaled. However, the norm of this vector will be essentially randomly generated. So we removed any norm information from the dataset, but we retained all the dimension information in the vector space. Of course, these approaches are not mutually exclusive, so both containers can be affected by introducing both types of noise at the same time. We can see this as a sense check, because this should essentially have random performance. In terms of the datasets we use for our experiments to validate the method, we actually use a set of datasets published by Kono et al. In 2018, which are English probing task datasets that kind of encompass different language domains such as surface information, morphology, syntax, and contextual incongruity. And so in our experimental setup, we compare two models, a static embedding model, i.e. GloVe, and a contextual embedding model, i.e. BERT. Both of them are just off the shelf, no pre-training, no fine-tuning for the tasks. But because the data sets that we use in our experiments are all annotated at the sentence level, we need sentence level embeddings because both these models provide just word embeddings. So we essentially just average the final layer in BERT and we average the word embeddings in GloVe to receive a sentence representation. For our probe and its evaluation, we use a multi-layer perceptron with just off-the-shelf default parameters. We frame the problem as a binary or multi-class classification task at the sentence level, and we use an AUC-ROC score as our evaluation metric, which means that a 0.5 score means that the model is not able to discriminate. And while we have some expectations of how the probe will perform in the different settings that we introduce, the big question is really about what will happen when we just ablate the norm of the vectors in the dataset versus what will happen when we only ablate the dimensions information, and how much will the scores drop when we do this. As an example result, we look at BERT on the Bigram Shift task, where we see that our random baselines perform as expected, so no information is encoded in these settings and they perform comparably to each other. The vanilla baseline obviously outperforms them, so it has learned the task quite well. And then when we ablate just the norm container, we see that there's a very, very small drop in performance, but this is actually not statistically significant as shown by our confidence intervals. However, when we ablate just the dimension container, we see that the score drops dramatically when compared to vanilla, indicating that most of this information relevant for this task was encoded in the dimensions and it has now been lost. However, when we also apply our norm ablation in addition to the dimension ablation, we see that the score actually drops further and only now reaches the random baseline performance that we've seen before. This means that while most of the information is encoded in the dimensions, something was left over when we removed this, and this obviously was the information encoded in the norm, confirming that the norm can also encode information for this task in BERT. And we observe this signal on some datasets in some other settings on some of the other encoders as well. So if we look at GloVe, we can see in our results that this result is replicated actually on the sentence length, word content, parse tree depth, and top constituent tasks, so surface level and syntactic tasks. Whereas in BERT, we see this in the Bigram Shift, odd man out, and top constituent task, which are kind of the contextual and a little bit of syntactic tasks as well. So the general findings of this tell us that the norm is a separate information container. It can carry information at the sentence level at least. The norm container can sometimes be empty, evidenced by the tasks that don't exhibit this behavior, and there can be redundancy between the norm and dimension containers. The different encoders utilize the norm to varying degrees, so GloVe encodes more syntactic information in the norm than BERT does, and different encoders use the norm to carry different types of linguistic information. So GloVe contains surface properties and syntax, where longer sentences are closer to the origin, and deeper syntactic trees are further away from the origin. BERT's norm contains more information on contextual incongruity, which is perhaps logical because it is a contextual encoder, and it positions incongruous sentences closer to the origin. In conclusion, to recap, we have introduced a methodological extension of the probing framework, probing with noise, which is an instrumentative and structural method that can identify the presence of information in the norm, thus providing geometric insight into which component of a vector encodes task-relevant information. We performed an exploration of the norm showing it can encode different types of linguistic information depending on which encoder is used. And we've also essentially done a comparative analysis of contextual and static embeddings, revealing that significant structural differences in their respective vector spaces, and demonstrated that contextual embeddings can partially encode contextual incongruity information in the norm. Thank you very much, and I'm happy to take any questions at any time. Please reach out any way you like. Thank you.